Hello. Um, in Algebra 1.5, this is a geometry review unit that we're getting ready to begin. Parts of it are not going to be review, so I really even shouldn't say review. I should say this is going to be a geometry review and preview. There are a few of you that are also in geometry, and so parts of this will be fairly easy for you, but if you're not in geometry right now, this kind of helps set the stage for geometry next year for you. But it's the sorts of things that you should know but might not know yet. In many cases, it's things we're going to use later in the year or might be helpful for things like the ACT, for example. And so we're going to start with actually sort of more of an overview of just logic and reasoning in general. And we're going to be looking at conjectures and trying to support or disprove them. Understand what conditional statements are. And once you know what conditional statements are, you're going to write what's called a converse, inverse, or contrapositive. This will very much feel like an English lesson, okay? Mostly writing. I don't know if you could just see the cat tail flick through the camera view. She decided to pay me a visit there for a second. So to start with just sort of what I want for all of you, of course, is to help you become better thinkers. So we start with sort of a abstract problem that's not really, or at least at first doesn't seem very mathematical. And so think about, if you pay attention in social studies class, think about all the ancient civilizations that you know. I would be ecstatic, and hopefully so would your history teacher, social studies teacher, if you could rattle off Mesopotamia, Egypt, Greece, India, China, and then you maybe also would throw in a couple of the slightly later to the game African civilizations or the Americas. But these are sort of the big five of the truly ancient world. And so think about those civilizations, kind of the big themes of social studies, and consider this map real quick. The red are the oldest civilizations that we have history about: ancient Egypt, Babylon or Mesopotamia, ancient India, slightly more recent in their development, but still really, really old, Greece and in China. And then more recent than those, you had 3 or 4 here in Africa, and then in Southern Asia or Southern Southeast Asia. Okay? And then I don't have the map of the New World for you because this is good enough. So kind of think about this. Alright? And then the problem I actually want you to think about is more like something you would see on Star Trek. It's, well, in the future, you're an archaeologist and you're working on a team that's exploring the galaxy, and you're trying to find planets that have conditions that are favorable or hospitable for life to develop, or it'd also be nice if they were good for humans too. We're going to be a little greedy, but hopefully not too bad. Okay, suppose you find a world where that's true. You find a planet that you think life could develop. What would you recommend that the captain do in terms of beginning their search for evidence of intelligent but not necessarily technologically advanced life? Okay, so you're looking for something vaguely like early humans. Maybe not actually humans, but maybe like smart reptiles or insects that can kind of walk and talk. So again, it's kind of like a sci-fi problem. So at this point, you kind of pause, you think about it, take the question seriously. Well, if you go back to what happened on Earth, what do all of these areas have in common? They are all developing near a water source, in most cases a river. And other than this one, for the most part, they're occurring in what you would call sort of the middle or center of the planet, in the part of the planet where the seasonal variations between summer and winter aren't quite as extreme. And so that you maybe go to, on a strange planet, kind of the parts of the planet that are like that, and see if there's any evidence that intelligent life is developed. In other words, that's where you would find the aliens, assuming they aren't going to be able to find you first, because they're also technologically advanced. And that's a great exercise in logic. Logic is sort of the art and science of reasoning, and logic, as most people sort of think about it, gets credited to sort of the ancient Greeks, but specifically a chain of 3 philosophers that you should have heard of: Socrates, Plato, Aristotle. And Aristotle gets the credit for creating sort of the form of logic that the Western world, which refers to Europe and the Americas, since the Americas were resettled by Europeans, well into like the 1800s. Logic is important in math, science, computers, technology, linguistics, and you could argue that it all goes back well over 2,000 years ago to Aristotle and the other ancient Greeks. So what is mathematics? And we've kind of had conversations along these lines before. It's a branch of knowledge. Some people would say discovered, some people would say created, some people would say invented by humans to help them solve problems, or some people like to think mathematics is sort of logical truths. Some people think of mathematics as being like a game where you've got these rules, which are often referred to as axioms or postulates, and then you kind of explore the consequences, which would get us into more like theorems or properties of like following those rules. Along that analogy, if mathematics is a game, then of course you have to learn the rules to play the game. But once you understand a game well enough, you can start like bending or breaking or tweaking the rules to kind of create your own game. And that's really what mathematics is in a lot of ways. Is up through high school, you're still just learning the basics. You're not really doing interesting cutting-edge mathematics in high school. It's like you're still learning the ABCs so that you might eventually get to learn how to, make up and spell words all on your own. A little bit more about logic here. Lewis Carroll was the pen name of actually a mathematician, and so it seems like nonsense, but a lot of Alice in Wonderland is actually quite logical. So here's an excerpt that I thought was kind of relevant. "I know what you're thinking about," said Tweedledum, "but it isn't so nohow." "Contrariwise," continued Tweedledee, "if it was so it might be, and if it were so it would be, but as it isn't, it ain't." That's logic. I thought that kind of sets the table nicely for us. Or something more like this. "All gobbledygooks are flibberflams. All flibberflams are purple yams." Well, that's complete nonsense, but assuming these 2 statements are true, it clearly indicates that also this 3rd statement would have to be true. All gobbledygooks are purple yams. All this or that, all that or some other thing, then all the this or that other thing as well. This might remind you of the transitive property. Here, this cartoon demonstrates sort of the same idea, but not done correctly. Penguins are black and white. Some old TV shows are black and white. Therefore, some penguins are old TV shows. And the caption, of course, here is "Logic is another thing that penguins aren't very good at." You might quickly identify what the difference is between this nonsense example that works and this nonsense example in the cartoon that does not work. The word all versus the word some. And kind of important there. So to actually get into like definitions, because I didn't think you need to write down a definition for logic. I hope you understand what logic is, even if you don't understand it exactly. Inductive reasoning, however, is a word that you might not really have any sort of concept of what that means. So inductive reasoning is the process of using specific facts, details, observations, or experiments to predict a general principle. The big idea here is you go from specific to general. You go from small little specific things to a big idea. An example of this you might be familiar of from a different academic setting is actually the scientific method is basically inductive in nature. Deductive reasoning is you use the general rules, principles, and other statements known to be true to reach a logically certain conclusion. In other words, you start with the big ideas and you work with those and reduce them down to I'm logically sound argument. I'm certain that this specific fact must also be true. And sort of the reference that I can make here that a lot of people might think of when they think of deduction is the Sherlock Holmes stories. You know, he had to use reasoning and sort of solve a crime, and he started with the generalities and moved to the specific. And so compare this to induction. You see, you're kind of building up to a theory, whereas here you're working your way down to make sure that you're right in a specific case based on this big general idea. A graphic that kind of ties this together better might be this one. So this is what I want you to really understand about just inductive reasoning and deductive reasoning. They're both examples of logic. If you start with a general principle and go to a specific example or instance, that's deduction. If you start with a specific instance and go to the general principle, like it worked this way here, so that must be how it always works, that's an inductive argument. Humans tend to start off life very inductive. Like babies figure out things inductively, and it is until you have a little bit better understanding of the world around you that you can be deductive in nature. Conjecture is an unproven prediction based on inductive reasoning. It's a statement that has not been proven true. It technically hasn't been disproven either. In science, you would use the word hypothesis in a very similar way. When you put a conjecture out there, it's usually based on knowing that in some examples it does seem to be true. The problem with examples is no, and this is very, very important, no amount of examples can absolutely prove something to be true. I mean, the sun comes up tomorrow has been proven true for countless tomorrows in the past. But that is actually no definite guarantee that the sun will come up tomorrow this next time. You just can't be sure. Fortunately, it only takes one bad example, one counter example, one example that goes against a statement to show that it's false. So you can never use examples to show something's true, but it's really easy to show something's false with an example. It just takes one. You find that sort of like one chink in the armor, make sure that it's false in that one case, and you're done. It's definitely false. So it's much easier to show things are false than true. And so at this point on the notes page, I have these two examples. It says, first example says, if P and Q are distinct prime numbers, then the number PQ or P times Q plus 1 is also prime. And when you first check that, it might seem reasonably true because you do, like, say, 2 times 3, 6. 6 plus 1, 7. Hey, 7 is still prime. 2 times 5 is 10. 10 plus 1 is 11. 11 is still prime. But an example that shows that it has to be false, a counter example, is actually 2 times 7. It would be 14. 14 plus 1 is 15. And 15 is 3 times 5, so it's definitely not prime. And so even though we had these 2 examples, and we probably found a few more that show that it's true, as soon as I find this one counter example, I know that statement is false. So this is a false statement. Whereas the second example is the sum of the first n odd natural numbers is n squared. We have to sort of give up at some point checking and say, well, it appears to be true. I've done several examples and it looks like it's true. The first odd number is 1, so you don't even really have to add it up. That is 1 squared. The first 2 odd numbers would be 1 and 3. When you add them together, you get 4, and that's 2 squared. So far it's working. The first 3 would be 1, 3, 5, which adds up to 9, which is 3 squared. The first 4, you would add up 1, 3, 5, and 7. You would get 16, and that would be 4 squared. You would add up the first 5 numbers, first 5 odd numbers, 1, 3, 5, 7, 9. You would get 25, and that is 5 squared. So now you maybe try it for 6, and 6 works. So you try it for 7, 8, 9. And if at any point you find a counterexample, you're done. But you can't ever quit. Cat, can't you quit? You can't quit either. Always curious, which is good, but it could be the death of you, as the saying goes. Alright, so a little bit more about like mathematical statements. There are basically only 4 different statements that we really care about in math. You can kind of reduce them down to these basic forms. Object X is property P. What I mean by that are statements along the lines of 5 is a prime number. Object X is 5. The property we care about in this case is prime numbers. Slightly differently, you might be concerned with every object of some type T has property P. And so sort of the example of this that's specific is every natural number is divisible by 1. The type T here is natural numbers. The property is divisibility by 1. The third format or form for a mathematical statement is about existence. There exists an object of type T having property P. So a specific example of that would be there is a largest 2-digit prime number. Let's see, the largest 2-digit number is 99, but that's not prime. 98. 97 sounds a little suspicious. I'd have to sit and think and work, and maybe I'd be able to convince myself maybe it's 97. And if it's not 97, I'd keep working my way down until I did find one. But eventually, I would know that it exists. I would find the largest 2-digit prime number. So in this case, the existence is sort of this idea of there is, and then the object of type T having property P. The type is prime numbers. The property in this case is being the greatest prime number that only has 2 digits. The fourth form that we tend to care about in mathematics is something along the lines of if statement A, then statement B. If an even number is prime, then the number is 2. If statement A is an even number is prime, statement B in this case is the number is 2. The rest of this lesson focuses on this if-then form because in terms of the actual structure, it's the most complicated in my opinion. These might be harder for you to understand just because you're so used to them that you're not even really used to thinking about them. So that if-then structure is what's called a conditional statement, and it has 2 parts, the hypothesis and conclusion. The part after the if is the hypothesis. The part after the then is the conclusion. It's often symbolized as P arrow Q, and we'll often read that arrow as implies. I could have done a slightly better job on this slide and made it a little more clear about what hypothesis and conclusion were and use the word implies there. A conditional statement is true if the conclusion is true, if Q is true, whenever P is true. The idea is that Q follows from P. The conclusion is a valid result of the hypothesis. And that if P then Q structure can actually be said a couple different ways. I actually said a few of them just without even really meaning to when I was talking about it. P implies Q. P is sufficient for Q. P only if Q. Q if P. Q whenever P. Q is necessary for P. All of those are equivalent to the same basic idea. If P, then Q. We'll try to avoid the ones that I feel like are the most confusing. There's the cat again. The most confusing for a beginner, which I've marked with a star. So let's kind of skip down the notes just a little bit to a couple examples here. So the tricky part is, if I give you some sentence that sounds like perfectly good mathematics, the absolute value of any real number is positive, realizing that with a little work you can turn that into an equivalent if-then statement. And in this case, I feel like probably the pretty good equivalent if-then statement is something along the lines of, if x is a real number, then absolute value of x is greater than 0. We have the hypothesis that we're dealing in real numbers, and we have the conclusion that the absolute value is positive. Notice that I did have to change this around a little bit in terms of the way it looks and the way it reads, but by no means have I changed the meaning. This actually happens to be a false conditional, and you can realize it's false pretty quick if you check 0. The absolute value of 0 is not going to be greater than 0. It's actually going to be equal 0. So maybe you could then try to fix this conditional, and you could strike out the word positive, the statement. If you want the statement to be true, you strike out positive and write non-negative, which is slight subtle difference. Non-negative includes 0. And then we could add the or equal to right here, and we fixed it. We would have taken care of that counterexample, and then we would start looking for another counterexample, and you wouldn't find one. Turns out 0 is the only number that caused trouble there. A right angle measures 90 degrees. Well, we know that's true, but how do you kind of put that in more of this if-then form? If an angle is right, then the angle measures 90 degrees, and we would kind of all agree, well, that seems to be true because that's the definition of right angle. And then now we kind of start working on our conditional statements, and one of the first things we're going to talk about is negation, which I want you to simply think of as the idea of not. Hold on. I thought I had this turned off. Apologize. Negation is the process of just sort of correctly inserting the word not. And so it's not P. Some books or sources would symbolize it with like the tilde, the little squiggle. And some would use sort of this shape, which I don't even know what to call that off the top of my head. I've forgotten. But you would still read this as not P, not P. So if a statement is, my name is Aaron, then the negation of that statement would be, my name is not Aaron, because that's the correct place to insert the word not. It is generally assumed to be true that a statement and its negation cannot be true at the same time. Sometimes referred to as the law of excluded middle. Everything's either true or false. It's kind of an interesting question. But we generally assume that yes, everything's either true or false. But there's no statement that's both at the same time. There's no statement that's neither. With a little work, you might be able to find a paradox, though, that shows that that's not always a good rule of thumb. But for most things we'll be interested in, it's either true or false, but not both. Converse, and not the shoe brand. You switch the hypothesis and conclusion, so Q would imply P. So if your original conditional statement is, if it is morning, then I eat Fruit Loops, a converse for that, again, you're not going to change the meaning, but you might have to change the wording slightly just so that it sounds reasonable coming off your tongue. I changed this one to, if I am eating Fruit Loops, then it is morning. By the way, I didn't put this conditional and converse are examples sort of as part of the definition. If you need to write them down, go for it, especially if it would help you understand the idea of converse. Double negation. Inverse. You negate the hypothesis and conclusion. Not P implies not Q. An example of this would be if you hate the conditional statement, if I'm lucky, then I'll win, and you correctly insert the word not into both the hypothesis and the conclusion, you have the inverse. And so the inverse of if I'm lucky, then I'll win is if I'm not lucky, then I won't win. I've kind of added the idea of not to both the hypothesis and conclusion. And then you kind of sort of mix this all together and you get what's called a contrapositive. And you do the inverse of the converse, or the converse of the inverse, or you switch and negate, and so it's not Q implies not P. An example of this would be if you take a conditional statement, if I drink Coke, then I get the hiccups. And so we got to try to switch the order of the ideas and correctly insert the words not. You would have the contrapositive is, if I do not have hiccups, then I did not drink Coke. And see, you've gone from looking at Coke implying hiccups to not hiccups implying not Coke. By the way, don't worry about whether or not these make sense or are true or false. We're just looking at taking a structure and sort of manipulating it. Our last type of statement is what's called a biconditional, and it's when the conditional and the converse are combined into one statement because they're both true generally, and you use the phrase if and only if, or instead of a one-way arrow, a double arrow, or occasionally at a higher level in like college you might hear a math professor say both necessary and sufficient. Most definitions can be written as a biconditional. So if it's true by definition, kind of like the right angle thing, you should be able to do a biconditional. Like, an angle is right if and only if the measure of the angle is 90 degrees. 90 degrees implies that it's a right angle. Right angle implies that it is 90 degrees. Sort of, I don't think you need to write this down, but I just want to kind of put it out there. Definition of definition. If it's a formal mathematical definition, you're going to explain what a word, or instead of word, potentially a phrase or a symbol, means using, only commonly understood or previously defined words, and you have to avoid ambiguous language, and it must work both forward and backward. So two segments are congruent if and only if the segments have equal measure. I've broken that apart into the two ideas. If two segments have equal measure, then the segments are congruent. The converse of that idea, the other half of the biconditional, if two segments are congruent, then the segments have equal measure. What's much easier than, instead of sort of repeating these two phrases over and over and over again as your definition of congruent, just sort of combine them together. Two segments are congruent if and only if the segments have equal measures. And then before we get into the final example, I kind of want to run through just a quick review here. And equivalent statements are either both true or both false. This is also kind of in that last example. So let's start with this harmless sounding conditional. If it is a poodle, then it is a canine. would be a true statement. The converse would switch the hypothesis and the conclusion. So if it is a canine, then it is a poodle. Well, that's false, because there are dogs that aren't poodles, like Labradors, for example. Inverse of the original conditional. If it is not a poodle, then it is not a canine. That is false. A Labrador is not a poodle, but it is a canine. It's a different type of dog. Finally, the contrapositive, you take the original statement, you switch poodle and canine, and you correctly add the word not. So if it's not a canine, then it is not a poodle. This one's actually true. If something's not a dog, then it's definitely not a poodle. So notice here that the conditional and the contrapositive were both true. It turns out they are equivalent. If a conditional is true, its contrapositive is still going to be true. Turns out switching the order and adding the word not to both halves keeps two statements logically equivalent. The converse and inverse are logically equivalent to each other, as in this example where they're both false, but they're not necessarily always the case. That all four are either true or false. So for this particular conditional statement that was true, the contrapositive was also true, the converse and inverse were both false. And sort of that's the end. But there is an example at the bottom of the page that I think you should try kind of on your own, about taking the statement about if an angle is right, then the measure of the angle is 90 degrees, and trying to do all these different manipulations. Like, can you do a converse, inverse, contrapositive? Can you do those three manipulations on your own? And think about whether each statement is true or false. And so I'll kind of leave it at that for right now. Thank you for your time. I hope that made sense. I think you'll agree that it didn't feel very much like a math lesson, because all we did was talk. We didn't really work anything out for the most part. So thank you for your attention. I will see you in class. See you next time. See you next video.